Okay, so tonight we're going to continue with what we were working on last week, except we're going to apply Bernoulli's theorem to fans and also friction loss through grain, moisture content in grain, psychrometrics, and equilibrium moisture curves as they apply to grain drying. It's one of those sort of classic ag engineering problems that even if there isn't a grain drying problem on the exam, there's going to be some type of drying problem. And so this is just a really good one to go through a lot of the core ideas behind drying. So let's remember what we were working on last week with Bernoulli's theorem, except this time we're going to look at it for fans. So I have a schematic here, a very crude schematic of a fan and a bin. So between 1 and 2 is the fan, and then there's a pipe between the fan and the bin. This is not to scale. And underneath the bin we have a plenum. So where you see the dotted line, that is the perforated floor that holds the grain. Number 3 is the top of the grain. And let's see, what else do I need to tell you? I think that's the crux of it for now. So then I've written Bernoulli's equation again. And the thing about air is that H1 plus the pressure divided by the specific weight at 1 is going to equal H3 plus the specific the pressure divided by the specific weight of the fluid at 3. So those two cancel each other out. And if we look at the velocity at 1 and the velocity at 3, those are 0. Let's go back there a minute. Because at 1, we're assuming the air isn't moving yet because it hasn't been through the fan. And at 3, that's a Q equal VA thing where the cross-sectional area is so large that the velocity is essentially 0. So what we're left with is W equals F, so that the fan work that goes in has to equal the friction loss through the system. And the work for a fan is going to be the static pressure plus the velocity head, which is going to equal the total pressure in the system, which has to equal F, the friction loss through the system. So Bernoulli's theorem looks a little different when we're talking about fans and air. And then if we want to know about power, there's 2 different measurements for power in air systems. One is the power based on total pressure, and then there's another power based on the static pressure. And the difference is the efficiency terms that you use. You can use the efficiency for total pressure or the efficiency for static pressure. Okay, so hold those thoughts for a minute. We're going to go through the friction loss through grain, and then we'll combine the two. So if you remember the schematic, we have the total friction loss through the system is going to be to the friction loss in that pipe that's connecting the fan to the bin. The friction loss due to expansion, because it's going from a pipe, the air is going from a pipe into the plenum underneath the bin, so it expands greatly, plus the friction loss through the floor, and then the friction loss through the grain. We know how to do the friction loss through the pipe. That's what we worked last time. It's just Darcy's equation. And we also know that the friction loss due to expansion is going to be V1 squared minus V2 squared divided by 2E. And as we did last week, this week we can make some assumptions. If V1 is the velocity in the pipe and V2 is the velocity of the air in the bin, we know that V1 has to be a lot greater than V2 because the cross-sectional area for V1 is a lot smaller than the cross-sectional area for V2. So then the equation reduces to V1 squared over 2G for the expansion. Now the friction loss through the floor, we have a couple different ways that we can compute this. If you have the textbook, then on page 29 is one equation, equation 2.38. Now this is an equation that we rarely use, so make a notation near it that it's only valid for when there's no grain on the floor. So put the bin, which I'm not sure when we would need that because we design these systems to be full. So we want to use equation 2.39 on page 30 of the Henderson, Perry, and Young book. And this is for grain on the floor. So it's the friction loss through the floor when there's grain on top of it. And you can see the equation there. It's 1.071 Pascal second squared divided by meter squared times V over O sub F times epsilon sub P over rho G. So this O sub F, percent floor opening, expressed as a decimal, that's usually given to you in the problem because it's going to be a physical reality of the bin system. And epsilon P is the voidage fraction of materials expressed as a decimal. And if it's not given, then 0.4 is a pretty good estimate for grains. Now the other way we can compute it is using this graph that's in the ASABE standards, and it is a function of the sheet opening percent along the bottom, and then the y-axis tells us the depth of clean shelled grain, or it says clean shelled corn, to give the equivalent airflow resistance as perforated metal sheet. So what this graph really tells us is if we didn't worry about the floor and we only treated it like grain, how much grain would that floor resistance add to the pile? And you can see from this graph that once you get above 7% opening in the floor really isn't a factor anymore. So it's really only when you have a really small percent opening in the floor that we worry about it. And then the friction loss through the grain, we can use equation 2.36 on page 29. And there are constants in there, and those were determined experimentally. You can get them from the standards, from ASABE standards, that I included with the material for tonight, or table 2.5 on page 30 of the textbook. We're going to get some practice using this. And in that equation, there's a correction factor, C sub F, and we use 1.5. Now these correction factors come into play because when they came up with all these for the equations, they used clean dry grain, so ideal conditions. And in reality, when you're putting grain in a bin, it's not dry and it's not necessarily clean. You're going to have a higher friction loss. So the standard procedure is to multiply by 1.5 to correct for that, the reality of the situation instead of the ideal situation. The other thing we can use, which is typically simpler if you're doing a problem by hand, is to use Shed's curves. And these are available in the standards, and also I included them in the handouts for today. On a Shed's curve, the x-axis is pressure drop divided by the depth of grain. On the y-axis, we have superficial velocity. Now that is going to be the air, so the volumetric flow rate of the air divided by the cross-sectional area of the. So it's usually expressed in meters cubed per meter squared second. And where I've usually seen it where they leave in the meters cubed per meter squared instead of simplifying it to meters, so that you realize it's superficial velocity and not just velocity. And when we use Shed's curves, again, we multiply the pressure drop by 1.5 for the correction factor. And that's talked about in the footnotes of Shed's curves. And if we want to convert to meters or feet of pressure loss, we're going to multiply by the specific weight of air. Now, one thing that I'll caution you on is to be very clear about what fluid you're using. So, you know, all those problems we did last week were water, and now we're in air. And it's pretty easy to get mixed up and start using the wrong specific weight. So just being very clear about what fluid you're working with. So here is the Shed's curves. And they have these curves for different grains. This is for shelled corn or wheat. So what we would do is come in along the y-axis with our superficial velocity. So in order to get that, we would have to know the cubic feet per minute airflow rate, and we'd have to know the square foot excuse me, of our bin, the cross-sectional area of the floor. So we compute our superficial velocity, and let's say it's 0.5 meters cubed per meter squared. No, that wouldn't work, would it? Because we're in English units. Cubic feet per feet squared second. And so what we go across until we run into the line that represents our grain that we're interested in, and then we drop down to the x-axis, and that'll tell us our pressure drop. So in this particular case, our pressure drop would be 0.002 inches of water per foot of grain. And then we would multiply by the depth of grain that we have in order to compute our overall pressure drop. And we also have Shed's curves in metric units, because we will see both. It's possible to see both sets of units on the exam. Okay, so let's try this. So we've got air that's going to be forced through a grain drying bin, similar to that shown before. The air flows through 5 meters of 0.5 meter diameter galvanized iron conduit, exhausts into a plenum below the grain, passes through a perforated metal floor at 10% openings, and is finally forced through a 1 meter depth of wheat, having a void fraction of 0.4. The area of the bin floor is 20 meters squared. Find the static and the total pressure when the volumetric flow rate is 4 meters cubed per second. So here is a schematic of what that problem said. We know our Q, 4 meters cubed per second. The length of that pipe is 5 meters. We have 1 meter depth of grain in the bin, definitely not to scale. The pipe is a 0.5 meter inner diameter. The floor has 10% openings. So the first thing we have to do, like before, is to compute the friction loss through the system. And in order to do that, we're going to look at every piece of the system. So we start out with the pipe, and then we have the expansion, remember, going from the pipe into the plenum. Then we have the friction loss through the floor and the friction loss through the grain. Okay, so if we want to know the friction loss through the pipe, what do we have to do? Well, we remember Darcy's formula, right? F times L over D times V squared over 2G. You guys should be experts at this now after our session last week. So what's the first thing we're going to do? calculate V, and then V squared over 2G. Perfect. Okay, I'm just getting my notes here. So V of the pipe is going to be Q divided by the area of the pipe. And our area is, our inner diameter is 0.5 meters. So if we run those calculations, we get that our velocity is 20.4 meters per second. Okay, and then the next thing we're going to do is calculate our Reynolds number. We can calculate V squared over 2G. I didn't happen to do it yet. So our Reynolds number is going to be dV rho over mu. Now, here's a question. What is the density of air? And where do we find it? Anybody know? Density of air? Or where to find it? We also need, while you're at it, we also need the dynamic viscosity of the air. Perfect. Page 20 in the textbook. We're going to look under air. There's a table 2-1. And if we do air at ambient temperature, the density is 1.202 kilograms per meter cubed. And the dynamic viscosity is 1.82 times 10 to the minus 5 Pascal seconds. So plugging those into our equation for the Reynolds number, we find out that it is turbulent. 6.7 times 10 to the 5 is our Reynolds number. Okay, so now we have to find out our epsilon over d so we can use our Moody's diagram. And I think it told us that we had iron galvanized pipe. I'm just checking to see if that one's in our table. So that's 0.15 millimeters. And then converting to meters, so that just so we have the same units on top and bottom so that it's dimensionless. Then we get 3 times 10 to the minus 4. Yeah, galvanized iron, 0.15 millimeters is in table 2-2. Okay, so then we have our Reynolds number and our epsilon over d, and we need to find our little using Moody's diagram. And if we do that, I got a little f of 0.015. And so plugging into Darcy's formula, there's v squared over 2g and L over d and RF. And I got 3.2 meters for that, that term. And next we do our expansion, v1 squared minus v2 squared over 2g. Should look pretty familiar. And plugging in, basically using just v1 squared because v2 is approximately 0 when compared to the velocity in the pipe. Now, when v2 stands by itself, we're not going to assume it's 0. We're going to use its actual value. But it's only as compared to v1 that it's negligible. We'll see that later in the problem where we actually have to use v2. So if we calculate this, we get 21.2. So now notice the relative magnitude of the expansion pressure drop versus the pipe. So the pipe was 3.2, and now the expansion is 21. So it has a bigger effect than the pipe did. Okay, so now we're on to the floor. And if we use equation 2.39, we need to know the velocity, the percent opening, and the void fraction. And I think those were all given. Oh, so we need to know, yeah, that's a good point. Let's go back up. That velocity is the velocity of the air that the floor sees. Well, now we're in the bin, right? So it's not going to be the velocity that we calculated before. It's going to be the velocity through the bin. So we have to recalculate the velocity to see what it's going to be when we're in the bin. We know our volumetric flow rate was 4 meters cubed per second. And the area of the floor is 20 meters squared. So now our velocity through the bin is 0.2 meters per second. And so you can see how this is negligible compared to the 20 point something that we calculated before, 20.4 meters per second. So we're going to take this velocity and we're going to plug it. Okay, we've got our opening expressed as a decimal, so it was 10%. We're going to use 0.1. And our void fraction, which was given as 0.4. And we're going to plug those into the equation. We know our density from table 2-1, and g is the metric gravitational constant. So plugging those in and doing the math, we get a floor friction loss of 2.3 meters. So that's the smallest one yet, right? That's even smaller than the pipe. So at some level, that starts to become negligible. Now we need to do the friction loss through the grain. And we have two different ways we can do this. One is to use the equation, and the other is to use Shed's curves. So we're going to do it both ways just to show you how to do it, and then you can take your pick. So friction loss but for the grain is equal to delta P divided by L. And then there's that formula, AV squared CF divided by the natural log of 1 plus BV. So A is given in the table. Let's see. It's, I forget, page 30. Is that what I said? In your book. Yep, page 30, table 2-5. If you look at wheat, the value of A is 2.7 times 10 to the 4. And then we have our velocity through the bin, because we're doing the friction loss through the grain, is 0.2 meters per second. You're going to square that. And we had our correction factor as before, which was 1.5. And now we've got 1 meter multiplied there because what we've done is multiplied through by L, because really 1 is delta P. So I just multiplied L to the other side, and that's what the 1 meter is. That's the height of the grain. I'm going to divide by that term the natural log of 1 plus B, and B comes from our table, 8.77 times V, which is the velocity. And so if we calculate that out, 1,599 pascals, which doesn't help us much because we need it in meters to compare it to the other ones. So what do we do to get it into meters? So a pascal is Newton per meter squared, and a Newton is a kilogram meter per second squared. We talked about this last week. So if we want to convert the pascals into meters, we're going to need to divide by Yeah, density to the rescue. I like that, Mark. Yeah, we got to divide by density, and so rho g. So we're going to divide by 1.202 kilograms per meter cubed and 9 times 9.81 meters per second squared. And if we do the unit analysis, we'll find that that comes out to be meters. And we get the friction loss through the grain is 135 meters. Now I want you to look at the relative magnitudes again. Remember the expansion, the friction loss due to expansion was 21 meters. And the friction loss through the grain is 135. And that's only 1 meter depth of grain. So in a lot of problems, it makes sense to neglect some of the other terms and focus on the grain because it's going to be the major factor in your friction loss. And we'll see a problem later where it makes sense to simplify the problem to that. But it's just good to notice what the relative magnitudes of these terms are. Okay, so if we want to use Shed's curves to get the friction loss through the grain, we're going to go to Shed's curve, the metric one. We're going to go on the y-axis at 0.2 meters cubed per meter squared second. That's the velocity, or the superficial velocity of the air through the bin. And we're going to the wheat curve. And then we're going to drop down to the x-axis. And when I do that, I get a value of 1,000. And on that, on the x-axis, are pascals per meter. So we have to multiply by the depth of grain, which is 1 meter. And we have to multiply by the correction factor because Shed's curves were done for clean, dry grain. So if we do that, we get 1,500 pascals. And converting to meters, we get 127 meters. So they're not identical, what we get in the equation and what we get through Shed's curves, but they're pretty darn close. Because, you know, a lot of these are essentially an estimate of what we have. Now, this is the place where the students all start to get nervous because they'll say, okay, well, if it's a multiple choice question, which way do we do it? And the answer is that the people writing the exam realize that it's a multiple choice, and so they will either tell you how to do it, you know, tell you which method to use, or they'll give the answers such that it's obvious which one it'll be. So they're not going to do 135 is one answer and 127 is another answer. It would be more like 10 meters might be one answer, 130 meters might be another answer, 500 meters might be another answer. And so then you're going to pick the one that's closest to what you, realizing that these are approximate methods because they're all done through experimentation. It's not, we're not at basic principles here. So we're not going to end up with just one right answer. Not sure how reassuring that is, but hopefully that's reassuring. So then we have to keep going and find our total. So we've got the friction loss through the pipe plus the expansion plus the floor plus the grain. And I essentially averaged the two that we had, the Shed's curve and the equation, and said, oh, let's call that 130 meters of pressure drop. So we get a total of 157 meters. Okay, but I think the problem, what did the problem ask us for? They didn't ask us for the total friction drop. They asked us for, I think, the, hang on, let me get back to it. I guess I could flip the slides. Okay. Find the static pressure when Q equals 4. Okay, so now we need the total pressure. So how do we get from friction loss through the system to total pressure? Well, if you remember, let's see if I have that. Nope. If you remember, with Bernoulli's equation for fans, W equals F. Right? That's basically what we got to. So we know F, so we know W, and W is the total work needed to be input to the system through the fan. So that would be our total pressure. So our total pressure is equal to 157 meters. And then if we want the static pressure, it's going to be the total pressure minus the velocity head. So it would be PT, which is 157. Let's see, we've got to check units here. But essentially the 157 minus the v squared over 2g, which is your velocity head. Remember, total head equal to the static head plus the velocity head. Okay, so that's essentially the answer for our equation, for our problem. Okay, so now we're going to let you do one. So this is problem 2.4 on page 45 of the textbook. We've got air, 21 degrees C, at a rate of 0.1 meters cubed per meter squared second. It'd be vertically through a crib of shelled corn that's 1.6 meters deep. Okay, so we've got shelled corn. So when they say the crib, basically well, I might also point out that I don't think you're given Q, but you are given enough to calculate Q. Yeah, so we have an answer of 16.8 meters per second. Yes. Or call it 17 meters per second. Okay, so what we're going to do next then, hopefully, is calculate the friction loss through the pipe, so we need to find our Reynolds number. Anybody need any more explanation on where that velocity of the pipe, velocity for the air in the pipe came from? If you do, just type it in. Otherwise, let me know when you have the Reynolds number. Yes, 336,824. And likely you're not going to have that exact number, but if you're somewhere around 336, you're good. Okay, so now then you've got to find your epsilon over d and find your little f. So let's check in when you've got your little f. And if you have questions on the Reynolds number, type them in there and I'll try to answer them. Okay, be brave. What's your little f? So epsilon over d should be 5 times 10 to the minus 4. You're going to use that with your Reynolds number and read it off your Moody diagram. Yes, 0.018. Great. This little f. This is where we usually run into a little dissension, so if you have questions on that, let me know. And then the next one should be the friction loss through the pipe. Anybody have a value yet for the friction loss through the pipe? Yes. Well, we need units, but I'm assuming you mean meters. And if that's true, then you're correct. Yeah, it's going to be around 10.5, plus or minus, depending on your rounding. Okay, so then we need the friction loss due to expansion. Yes, 14.7 meters. Perfect. Okay, now try a new one, F of the floor. Let's use the equation. I think we have corn. So you're going to have to find A and B. Because I don't, oh, we don't need that, right? No, we don't. We just need the opening and the epsilon, yeah. So you got everything you need. Let me know when you have a value for the friction loss through the floor. You can kind of check yourself too, because it's likely going to be smaller than the friction loss due to expansion. I mean, that's not what I meant. The friction loss due to the, hang on. Yeah, due to expansion, the 14.7. If it's not, you've probably done something wrong. All right, who's going to jump in and give me a number for the floor? So I think really the only questionable term is that V divided by O sub F E sub P, right? So V, we're going to use the superficial velocity because we want the velocity through the grain, since we're finding the friction loss through the floor. And O we were given. And we weren't given the epsilon, but we know what to assume if we're not given it, right? Anybody got a guess? An educated guess. Or the correct answer. I'll take either. Yes, 0.6 meters. Okay, so we've got our floor. And the next thing we need to do is the friction loss through the grain. So I recommend using Shed's curves. If you've got them there, they were, one of the handouts. And we know our superficial velocity, right? It's 0.1 meters cubed per meter squared second. And that's going to be what we go into the y-axis with. Go straight across to corn. And there is one that is labeled shelled corn. So you find that line and then you drop down to the x-axis. So using Shed's curves, what are you getting for the pressure drop per unit depth of grain? So in pascals per meter. Anybody want to volunteer what they're reading off the graph? Okay, I got a bigger number than that. Are you on the metric one? So you're going to go in at 0.1, so about halfway up the metric one, and then you're going to go straight across to, I don't know, it's about 2/3 of the way over. You'll see the shelled corn line. It's between rescue grass seed, soybeans, and shelled popcorn yellow pearl. And then you're going to drop straight down to the x-axis. Yes, 150 pascals per meter. And then we get to multiply by the depth of grain and then convert it into meters of pressure drop. So we're going to divide by the density of the fluid and the gravitational constant. Okay, so go ahead and convert that into friction loss through the grain, and don't forget to multiply by your correction factor, which is 1.5. So you can take your 150, multiply by your depth of grain, multiply by your correction factor, and then convert the units to meters of air. So let me Great. Yep, 30.5 meters is the friction loss through the grain. Okay, so now we're ready to add them all up. So let me know when you have your total friction loss through the system. Anybody have the total friction loss yet? I know you've got this. This is just adding up numbers. Yep, 56.4 meters. Okay, so now we're wanting to know what is the power requirement. So now we have to use our power equation. And if you remember from slides several back, that was WQ rho G over E, the efficiency, is the power. So if we take our total friction loss, that's going to equal to our total pressure. So that's W times Q, which you had to calculate in the beginning, the flow rate through the system, volumetric, and then rho G, and divide by the total efficiency, which is 0.7. And then figure out what units you have. So let me know when you've got a number for power. Or if you have questions on what I just said. Anybody have an estimate for power required? Come on, be brave. So you're going to multiply your 56.4 times your volumetric flow rate, which is 1.2 meters cubed per second, right? Times your density of the fluid, which is 1.202 kilograms per meter cubed, and G, 9.81, and then you're going to divide by your efficiency, which is 0.7. $1140 Newton meters. That's really close. Your units are off by a second. So it should be Newton meters per second. And a Newton meter is a joule, right? And joules per second equals watts. So you've got watts. Now your number is a little bit higher than what I got. Let's see, I got 943. Let's see, did you use the 56.4 meters for your W? Then 1.2 for your Q. Of course, I could very easily have typed it in wrong, so. What are other people getting for that number? Well, that's pretty darn close to 1140, isn't it? Okay. Um, 1330. Wait a minute, that's higher. Hang on, let me punch in these numbers here. We've got 56.4 times 1.2 times 1.202 times 9.81. I got 798 divided by 0.7. Yeah, 1,140. All right, good. So, yeah, okay, 1138 the second time, yeah. Yeah, I'm good with the second time. All right, well, if you followed all that, I think you're doing pretty well because there are a lot of steps to that problem. And if you want to check yourself, there's a second half to problem 2.4, and they ask you what is the power requirement if you have a bigger pipe. So I would recommend that you just put away your notes from what we just did and try it again on your own. And I got an answer of 708 watts for the second part of the problem, if you want to kind of check yourself. And feel free to email me if you have questions on that. But now we're going to go on. Changing subjects a little, we'll circle back to the fans. But now we're going to talk about moisture and psychrometrics. And the first thing we're going to review is moisture content in biological materials. You know, the biological materials are going to gain moisture or lose moisture depending on what environment they're in. And we quantify the moisture in the material either on a wet basis or a dry basis. And these equations are on page 273 of the text. So this book uses a little m for wet basis and a big M for dry basis. And the wet basis is the weight of the water divided by the weight of the water plus the weight of the dry matter. And so you can think of a biological material kind of like a sponge, and if we could take all the water out of it and just have that really dry sponge, that's what the weight of the dry matter means. So if we had a bushel of corn and we took every last drop of water out of it, what would it weigh? That's the W sub D. So really it's the weight of the water over the total weight. And then on a dry basis, we have the weight of the water divided by the weight of the dry mass, or the dry matter. The other thing that's helpful to know is standard bushels. In the ASABE standards, standard bushel of corn is defined as 56 pounds at 15% moisture on a wet basis. Soybeans weigh 60 pounds per bushel at 13.5% moisture on a wet basis. Those are something else that I write on the inside of my textbook. Okay, so we can use this information to determine how much water needs to be removed to dry the grain. So let's say we have 2,000 bushels of soybeans and they're coming in from the field at 25% moisture on a wet basis. How much water must be removed to store the beans at 13.5% water? Okay, so remembering, oh, you're not seeing the slides. Hang on. I don't know how to make that happen. Let me just see if I can. I'll stop sharing and start sharing again. Let's see if that works. Now I'm not seeing them. Oh, I'm not sure what to do here. Let's see. I didn't do anything and it just stopped. Okay, I don't know what to do. Now it's stuck. It won't even let me start the sharing or stop the sharing. Yeah, Gloria's suggesting maybe you could download the slides and follow along. But shoot, I wish I could figure out why it's not working. Okay, well, I'm just playing around. I'm not really getting anywhere here. Okay, so let's go on. Sorry about that. I wish I understood this software better. Okay, so remember that the grain is made up of dry matter plus water, and the amount of water changes, but the amount of dry matter in bushels is constant. And so that's the secret, if there is one, of working these problems, is that the dry matter in bushels is constant. Okay, so we know that a standard bushel of soybeans weighs 60 pounds, and that's going to be our total weight. And that's going to have a water content of 0.135, or 13.5%. So we can solve for the amount of water in that standard bushel just by multiplying. So if we multiply 0.135 by 60 pounds, we get 8.1 pounds of water. Oh, Justin's saying that the slides aren't hyperlinked anymore. Can everyone access them? Yeah, I don't know. They're under handout 1. Hopefully that's helpful. Oh, this is nice. You guys are very helpful. Okay, so if we know the amount of water in a bushel, which is 8.1 pounds, then we could subtract that from 60 pounds and find out how much dry matter we have. So in a standard bushel of soybeans, there's 51.9 pounds of dry matter. And this is important because now we can use that information to find out how much water we need to remove when the soybeans are at 25% moisture content. So going back to our original equation, we've got the moisture content on a wet basis is 0.25, and that equals the amount of water in the sample divided by the total weight, which is the water plus the dry matter. And the water is going to change, and so there's something that's changing in the numerator and in the denominator. So we need to cross multiply and solve for the weight of the water. So if we just do the algebra there, we find out that the weight of the water in the bushel at 25% moisture content is 17.3 pounds. So then by subtraction, we can find out how much water we need to remove. We have 17.3 pounds per bushel in the wet grain, and we want 8.1 when we're done drying. So we need to remove 9.2 pounds of water per bushel. And we've got 2,000 bushels, so we need to remove 18,400 pounds of water per bushel. We're going to combine this with our psychrometrics here in a minute, and then we're going to be able to find out how much airflow we need to send through the grain in order to remove that much water. Okay, so let's have you try it. How much water needs to be removed to dry shelled corn from 23% wet basis to 15% wet basis if we have 1,000 bushels? And you'll remember that a standard bushel of corn should weigh 56 pounds at 15% moisture content. So the first thing you're going to do is find out how much water is in the standard bushel. Right, so you're going to write your equation that 0.15 equals the mass of the water divided by the total weight, which is 56 pounds. And that's how much water is in the standard bushel. So let me know when you know how much the dry matter is in a bushel of corn. Well, I got 47.6, but yes, pounds. So I got, sorry, I think that's noisy. Okay, I got 8.4 pounds of water. So then 56 minus 8.4 is 47.6 pounds of water. Oh, never mind. We got the same number. Okay, so if we have 47.6 pounds of water in a bushel of corn, no, sorry, 47.6 pounds of dry matter in a bushel of corn, and it's coming in at 0.2 at 23% wet basis, how much water do we need to remove to get it back to the standard bushel? So now we need to find out how much water is in a bushel when it's at 23% moisture content. So your equation should look like 0.23 equals the mass of the water divided by the mass of the water plus 47.6 pounds. And then you're going to solve for the mass of the water. Anybody? Yes, 14.2 pounds. Okay, so that's how much water's in the wet grain, and we know that the dry grain has 8.4 pounds in it, so how much do we need to remove? So we're going to subtract those two. And if my math's right, that's 5.8 pounds times 1,000 bushels. So 5,800 pounds of water to dry that 1,000 bushels. Questions on that? Okay, so if you have your psych chart, it's time to pull it out. We're going to review this real quickly. We're going to put all these things back together when we get to the grain drying problem. So if you know two properties of an air-water vapor mixture, then you know all values. This is the great thing about the psychrometric chart is that you only have to know two properties, and we can come up with all the properties of the air-water vapor mixture because two properties establish a unique point on the psych chart. Okay, so there's a lot of lines running around, and if you haven't used these for a while, let's just quickly go through them. So the vertical lines are the dry bulb temperature. So you should be able to look along the bottom and see dry bulb temperature and just follow that up and down, straight up and down. The horizontal lines are the humidity ratio. And you follow those. So horizontal lines, to get the humidity ratio, you follow those directly over to the right and read off the right axis. And if you want dew point temperature, you go straight to the left and read off the curved axis there. Then the slanted lines are wet bulb temperature and enthalpy. And these are the lines that slant from the bottom right to the top left. And then there's some other slanted lines on there that they're less steep, I believe that's right, than the wet bulb temperature lines and the enthalpy lines, and those are your specific volume of your air. Okay, so we're going to practice reading our chart. If we have a dry bulb temperature of 70 degrees Fahrenheit and a wet bulb temperature of 60 degrees Fahrenheit, then what's the enthalpy, humidity ratio, specific volume, and dew point temperature? Okay, so the first thing we're going to do is find 70 degrees Fahrenheit on the x-axis and find its vertical line. And wet bulb temperature is along the curved axis on the left. So find 60 degrees on that curved axis. And now you're going to follow those constant enthalpy lines or wet bulb lines, so the slanted ones, and you're going to run down the 60 degree line and up the 70 degree line until they intersect. And you're going to put a point there on your psych chart. And then we're going to read off the values. So if we want enthalpy, remember that those are the slanted lines, the lines that slant from the bottom right to the upper left. So basically, if you just run up that 60 degree Fahrenheit line for your wet bulb temperature, you should be able to see the enthalpy. And enthalpy has units of BTU per pounds of dry air. And you should be seeing a number of about 26 BTUs per pound of dry air if you're in the right spot on your psych chart. Okay, and then we want to find the humidity ratio. So we go back to our dot that we made, and humidity ratio is straight to the right. So we follow the line horizontal to the right until we can read the humidity ratio, and it's about 0.0088 pounds of water per pound of dry air. Okay, now the next one we're asking for is specific volume. So you should be able to find the lines on your chart that are in cubic feet per pound of dry air. And those are the other slanted lines, not the enthalpy lines. And you'll notice that our point is not on a line, so we have to kind of estimate between the lines. And I got 13.55 cubic feet per pound of dry air is the specific volume for that point. And then the last one that we're asking for is the dew point temperature, and that one is straight to the left. So go back to our point, and we follow the horizontal line to the left, and where it intersects the curved axis is the dew point temperature. That's 100% saturation, and I read off 54 degrees Fahrenheit. Okay, but that's not really where the power of the psych chart comes in. The power of the psych chart comes in from these psychrometric processes. So we can estimate like how much heat we need to add, how much heat we need to remove. So we can actually size equipment off the psych chart. So if you remember these processes, sensible heating, so just the heat addition, not the latent part, is horizontal to the right. So if we say we want to heat the air from 50 degrees to 70 degrees, we would start at our point and then move straight over to the right to heat it. And then that new point is going to have all its psychrometric properties, and we'll know those. Sensible cooling is the same thing, except we move horizontally to the left. Now, one thing to notice when we're moving straight across, our humidity ratio is not changing, right? But our relative humidity, which are those curved lines on the chart, you can find the relative humidity, they change. So the relative humidity changes when you heat or cool, but you still keep the same amount of water in the air. And that's because relative humidity is a measure of how much water you have in the air compared to how much the water the air can hold. And when you heat the air can hold more, so your relative humidity is different. Okay, but the one we're really interested in the context of tonight, is evaporative cooling. So evaporative cooling is the process that happens when we blow air over grain, and the air picks up the water from the grain. And evaporative cooling is moving up the constant enthalpy line. So if we have a point and then we move straight up the constant enthalpy line, that's an evaporative cooling process. So let's do an example of that. Let's say we have a grain dryer and it requires 300 meters cubed per minute of 46 degrees C air. The atmospheric air is at 24 degrees C and 68% relative humidity. How much power must be supplied to heat the air? Okay, so our solution, we're going to start at point 1, which is 24 degrees C and 68% relative humidity. So there's two properties, right? And they're going to give us a unique point on our psych chart. And if we find that point and then go up the enthalpy line and read it, we see that that point is at 56 kilojoules per kilogram of dry air. So we switch to the metric chart now. And then we know we want to heat the air. And so that tells us that what we're going to do is move directly to the right. until we get to 46 degrees C. And as you notice, since we know we're heading horizontally and that we want to end up at 46 degrees C, that uniquely identifies our stopping point also. So we know where point 2 is. And we can go up and read our enthalpy from that, and we get 78 kilojoules per kilogram of dry air. And the other thing that we can find is the specific volume of the air. And that is 0.922 meters cubed per kilogram of dry air. I'm assuming that is the specific volume of the first point, although you'll have to check me on that one, because there's two different specific volumes, right? When you heat it, it's going to expand. Okay, so we know our enthalpies, and what we want to know is our change in enthalpy, because that's going to tell us how much heat we need to add to the air. So the energy that we need is the difference, 78 minus 56 kilojoules per kilogram of dry air, or 22 kilojoules per kilogram of dry air. And then the amount of energy we need then is delta H, change in enthalpy, times the volumetric flow rate, which was given, divided by the specific volume. And we got to check our units. So we multiply 22 kilojoules per kilogram of dry air divided by our specific volume, which is 0.922 meters cubed per kilogram of dry air, times 300 meters cubed per minute, and times 1 minute over 60 seconds. And that's 119 kilowatts. So you see we can use the psych chart to determine how much of a heater we need. Okay, so we've done moisture content, we've done the psych chart, we've looked at processes on the psych chart, just a very quick review. Now we're going to review equilibrium moisture content curves. Okay, and these are important because when a biological product is in a moist environment, it will exchange water with the atmosphere in a predictable way, depending on the temperature and relative humidity of the moist air surrounding the biological product. And the compilation of this information are called the equilibrium moisture curves for each product. And we need this because when we're drying, we can't get all the water out of the grain. We can only go to the equilibrium moisture content of that grain in that environment because we just don't have the driving force to get all that water out of the grain under those different conditions. So the next slide shows an example of these equilibrium moisture content curves, and they're in the ASABE standards. And there are different curves for different temperatures and different grains. So I'm showing you the equilibrium moisture content curves for yellow dent corn. And the way we read these is we go on the x-axis and we find the relative humidity of the air that the grain is in. So let's say it's 60 degrees relative humidity. And let's say it's 30 degrees C. So we go up to the intersection of 60 and 30, and then we go to the left to our y-axis, and we find out that the equilibrium moisture of that grain is about 12%. So we cannot dry that corn down further than 12% in an environment where the relative humidity is 60% and the air is 30 degrees C. That's our minimum. Now, we use these in our drying problems to establish the second point on the evaporative cooling line. So when you're moving up the evaporative cooling line, at some point you'll get to saturation, right, where the air is saturated and can't take any more water. But we don't usually get that far when we're drying grain because we can't remove enough water from the product to saturate the air under all conditions. So sometimes we're exhausting the air at a lower relative humidity because we just can't get any more water out of the grain. So we need to know what that second point looks like. What does the exhaust air look like? Okay, so stay with me. It sounds complicated, but it's really not. So we're going to do this by selecting the equilibrium moisture content curves for the product of interest. And then on the y-axis, we're going to draw a line straight across, a horizontal line, at the desired final moisture content of the product. This is usually given in your problem. And then at that point, we'll have 4 temperatures and relative humidities from the equilibrium moisture content curves. So there's a sketch on the next slide. Let's say we want to end up at 15% water content in the grain when we're done. So then we draw the horizontal line, and then at the intersections, which my arrows have shifted a bit, but at the intersections we drop down and we see, okay, we've got at 0 degrees C we have 60% relative humidity. At 10 degrees C we have about 68% relative humidity. 30 degrees C we have about 75% relative humidity. And 80 is usually too high for us to care, or 50. I guess it's 50 degrees C. Okay, now you're going to take those 3 or 4 points, the combinations of temperature and relative humidity, and you're going to draw those on your psych chart. And they'll be roughly in the shape of a relative humidity curve. So you're going to sketch in between those points. And where this curve intersects your constant enthalpy line, that's going to be the exhaust air. That's going to be the state of the exhaust air. So, okay, so we're going to draw those points on your psych chart. And I show an example here on the next slide of the constant enthalpy line starts at that red dot and goes up the dotted line. And only 2 points that we get from the equilibrium moisture curves will actually span the line that we're interested in. So those 2 points are shown. And if we sketch in a curve between those 2 points, we'll find the sketch in the curve. And so where that intersects with the dotted line is going to be our endpoint, our exhaust air. And that's what the next slide says. Where this relative humidity curve intersects your drying process line represents the state of the exhaust air. And that's the second red dot. All that to find that red dot. Okay, so let's try it. We are drying corn to 15% wet basis with natural ventilation. We're using outside air at 25 degrees C and 70% relative humidity. What will be the dry bulb temperature and the relative humidity of the exhaust air? Okay, so we're going to go into our equilibrium moisture content curves, and we're going to draw a horizontal line at 15% wet basis, at 15%. So on the y-axis, we're going to go into 15% and draw a line straight across. And then we're going to get, at 0 degrees C, it's 60% relative humidity. At 10 degrees C, it's 68% relative humidity. 30 degrees C, we have 75% relative humidity. And at 50 degrees C, we have 82% relative humidity. Well, those aren't all going to span the drying line. So our drying line starts at 25 degrees C and 70% relative humidity. So on our psych chart, we're going to draw our dot at 25 degrees C and 70% relative humidity. And we're going to draw our dotted line in up the constant enthalpy line. And then we're going to plot the temperature relative humidity points on the curve. Let's see, I have that. So I plotted 10 degrees C and 30 degrees C, those 2 points, and drew in the relative humidity type curve between those 2 points. And where that intersects my constant enthalpy line is where my exhaust state is going to be. And on my psych chart, that looks like a dry bulb temperature of 24.2 degrees C and a relative humidity of 75%. So that gives us the exhaust state of the air. Okay, so let's use all this stuff that we just learned or remembered. Okay, so here's an example problem. We want to know how long it would take to dry 2,000 bushels of soybeans from 20% moisture content to 13% moisture content with a fan which delivers 5140 to 9,000 CFM at a ½ water static pressure. The bin is 26 feet in diameter and outside air, which is 60 degrees Fahrenheit and 30% relative humidity, is being blown over the soybeans. Okay, so how do we approach this problem? We break it into steps. And this is why I think these problems are good potential problems for the PE, because they can be broken into steps and turned into multiple choice small problems. Okay, so the first thing we're going to do is determine how much water needs to be removed from the soybeans. And that's our wet basis moisture content type problem. We're going to determine how much water each pound of dry air can remove. And we're going to do this from the psych chart. That's a process on the psych chart. Calculate how many cubic feet of air are needed. And that's just algebra, because that's a units thing. Then we're going to determine the fan operating CFM. Okay, this sounds a little bit like the operating point on the pump. So this is where we're going to take the system curve and the fan curve, and where they intersect, we're going to find the Q, cubic feet per minute. And then from this cubic feet per minute, we know how many cubic feet we need. We can determine the time needed to dry the soybeans. That's just a units thing again. Okay, so we got a lot of work to do in 15 minutes. Okay, so how much water must be removed? So we have to calculate that. We want to go from 20% to 13%. Now, this is a little tricky because the standard bushel is at 13.5%. So we have to calculate the standard bushel first. And the standard bushel has a dry matter content of 51.9 pounds. Okay? So we're going to dry it a little bit drier than the standard bushel. And we need to find out how much water is in that drier bushel. So at 0.13, or 13%, we have the mass of the water divided by the mass of the water plus the dry matter in the bushel, which is 51.9 pounds. Then we do our algebra, and we find out that when the soybeans are dry, they have 7.76 pounds of water in them. Okay, now we want to know how much water the soybeans have when they're coming to us, wet from the field. So they're at 20%, and we know they have 51.9 pounds of dry matter in them. So if we do the algebra there, we get 12.98 pounds of water in each wet bushel. So then the amount of water we need to remove is the difference between the wet bushel and the dry bushel. And that is 5.22 pounds of water per bushel. And we have 2,000 bushels, so we need 10,440 pounds of water removed. Okay, so that's almost exactly like the previous problem. Okay, so now we need to know how much water each pound of dry air can remove. And this is a psychrometric process. So we need to know, if you look at pounds of water per pound of dry air, that's the humidity ratio. So that's the value that's all the way to the right on your psych chart. So we need 2 points, and we need to find out the difference between them, right? So our first point is going to be our ambient air, which was, what, 60 degrees? Let's see. The ambient air was 60 degrees Fahrenheit, 30% relative humidity. That's point 1. And we need to find point 2 by going into our equilibrium moisture content curves for soybeans and drawing in a horizontal line at 13%, and dropping down and getting our points that we're going to add to our psych chart in order to find our exit air. So if we do that, the air is going to exit at 52 degrees Fahrenheit and 68% relative humidity. That'll be a good practice for you to check that, see if you get those answers. Okay, so now we need to know the change in humidity ratio. So we go straight across from point 2, and we get 0.0056 pounds of water per pound of dry air. And if we go straight across from point 1, or our ambient air point, we get 0.0033 pounds of water per pound of dry air. So each pound of dry air can remove 0.0023 pounds of water, because it's going to be the difference in your humidity ratio. Now we need to remove about 10,500 pounds of water. I rounded up. And we know each pound of dry air can remove 0.0023 pounds of water. So we just do the math there, keeping track of our units. So you'll notice on this problem, pounds of water and pounds of dry air, they're all subscripted so that we don't get confused. If we just put pounds there, we wouldn't know whether we were talking about water or dry air. And we need to cancel our pounds of water. So we need 10,500 pounds of water to be removed, and each pound of dry air can remove 0.0023. So we need 4,565,000 pounds of dry air. Okay, so that's step 2. Step 3, we need to determine the cubic feet of air needed to remove that water. Okay, so this is going to be another computation based on our specific volume of air. Now, here is a helpful hint, because students are always asking me, what specific volume do we use? Excuse me. The specific volume that you use is the point at which the fan sees the air. So in this case, we're blowing ambient air, right? So we want the specific volume of the air at the ambient point. We don't care about the specific volume after it's been blown through the grain. So at point 1, we read 13.2 cubic feet per pound of dry air off our psych chart. And just doing that calculation, we get 60,260,000 cubic feet of air. Okay. Now, we need to determine how much, determine the fan operating speed. So this is should be very familiar based on our pump. We need a system characteristic curve. Now, with the pumps, that's fairly complicated because, we use the whole Bernoulli's equation. With the air and the grain bins, if you remember, the largest term on the friction loss was the grain. So we're going to simplify this problem, make the assumption that our system characteristic curve can be approximated by the friction loss through the grain. And we can find that curve by going to Shedd's the sheds curves and looking at a bunch of different airflows and figuring out what the pressure drop is. And then that'll give us the F of grain. That'll give us that system characteristic curve. And they gave us the fan curve in the problem. They said the pressure drop of ½ an inch between the, what was it, 5,300 and 9,000 CFM. Okay, so we can draw those, and where that intersects is going to be 6,300 CFM. Okay, and now all we have to do from the CFM of the fan and the cubic feet of air we need, we're just going to determine the time we need to dry the soybeans. So that's just a units problem. So we know we need 60,260,000 cubic feet of air, and the fan can supply it at 6,300 cubic feet per minute. So just dividing those two, we get 9,565 minutes, or 159 hours, or 6.6 days. And you say, wow, that's a really long time. But if you look at the problem, we weren't heating the air, we weren't really giving it any kind of driving force to dry the grain. So this is essentially just drying with ambient air. It's going to take about a week to dry those 2,000 bushels. Okay. Now, I wanted to do a quick example that's not grain, so you can see that really the process applies to all of these drying problems. So if we have ambient air at 32 degrees C and 20% relative humidity, we're going to heat it this time. We're going to heat it up to 118 degrees C in a fruit residue dryer. So we're going to basically dry fruit. And the flow of ambient air into the propane heater is 5.95 meters cubed per second. So we're heating it up, and the drying is to be carried out from 85% water content to 22% water content on a wet basis. And here they're giving us the state of the air when it leaves the dryer. It's 40.5 degrees C. And then the question is, determine the airflow rate of the heated air. Okay, so when heating the air, mass flow rate is conserved, but volumetric flow rate is not, which makes sense when you think about it, right? Because when you heat air, it expands, and so the volume changes, so it's not conserved. But the mass is. So we know we had 5.93 meters cubed per second at a specific volume of 0.875 meters cubed per kilogram. And we know that because we were given the psychrometric properties of the air where we knew the flow rate. So if we convert that to mass flow rate, we get 6.8 kilograms per second. Now we can use that anywhere. So at point 2, where the air has expanded to have a specific volume of 1.125 meters cubed per kilogram, we know we've got 6.8 kilograms per second mass flow rate, so we can calculate the volumetric flow rate of 7.65 meters cubed per second. Now the other thing to notice is that 118 degrees C is not on your psych chart. We have to have a high temperature psych chart in order to do that. And you can get those off the ASHRAE website if you don't have one. And I would just recommend getting a high temperature one, because if you end up with any problems about drying, like in the food industry, you're going to get these higher temperatures. Okay, so now we can determine the relative humidity of the air leaving the dryer. So how are we going to do that? We start out at 32 degrees C, and we're going to heat it up to 118. So they gave us the relative humidity too. So we've got that 0.1 at 32 fixed in place on our psych chart, and we know we're going to heat it to 118 degrees C, which fixes our second point, and we're going to move up the constant enthalpy line because it's a drying process. And they told us that the exit air is at 40.5 degrees C. So that fixes our third point. So we can draw those onto our psych chart and just read off the relative humidity, which is 78%. Now we need to determine the amount of propane fuel required per hour. So this should give us the question should give us a hint that we want to use the enthalpy, because propane, the heating value is going to be in kilojoules per kilogram of fuel, and the property on our psych chart that's in kilojoules is the enthalpy. So if we back up, we see that the fuel is needed between 0.1, the 32 degrees, and 0.2 or 0.3. Those are the same, right? They're on the same enthalpy line. So we need the difference between those two enthalpies. Let's get back to that. Oh, I'm going the wrong direction. No wonder. Not that you can see them anyway. So we get back to the propane. We can look the heating value of propane up in a handbook, and it's 50,000 kilojoules per kilogram of fuel. And we know our enthalpy at the second point is 140 kilojoules per kilogram of dry air. At the first point, it was 49.5. So the difference times the mass flow rate, because we got to get rid of that kilograms of dry air, is going to be 615.4 kilojoules per second. And based on the heating value of the propane, that's going to be 44 kilograms of propane per hour. So just from the psych chart, we're able to figure out what kind of fuel we need. Okay, the amount of fruit residue dried per hour. Now, this problem is different than the grain because we don't have anything like a standard bushel. So we're going to do everything on a kilogram basis. So at 85%, we know it's coming in at 85%. That leaves 0.15 of every kilogram is dry matter. So then it's leaving at 22%. And so if we calculate the amount of water left in the fruit at 22%, it's going to be 0.0423 kilograms of water. So this problem is everything is done per kilogram of wet material. So we need to remove 0.808 kilograms of water per kilogram of wet residue. And we know our change in humidity ratio, which is 0.032 kilograms of water per kilogram of dry air. And if we multiply that by the mass flow rate and by the amount of water we need to remove from each kilogram of wet residue, we can calculate how much we can process, which is 970 kilograms of wet fruit per hour. Okay, so I realized that we went through those last couple problems pretty quickly, so I would recommend going through them more slowly and making sure that you know where we got all those numbers. And when you're fairly confident with that, then here's another problem for you to work. And this is a grain bin problem. And I have the solution, which I will ask Mark to post so that you can check it. And I'm going to, again, give you my email so that, if you have any questions, you can email me. And I can hopefully answer them. And the other thing I want to encourage you to do is work other problems that are in the Henderson, Perry, and Young book, especially in the chapters that in which we were working. And if you want to check answers, feel free to email me. I've got most of the answers to those problems. Yeah, but there's nothing like just working a lot of problems to be able to see what kind of question they're asking. You can see from these grain bin problems that you're going to have to work several in order to see, oh, if they've given me this and they've given me this and they're asking me for time to dry, then I know how to do that. You're kind of stepping into the problem in the middle. They'll give you sort of some of the intermediate answers and then ask you to find another answer. So how we've broken it out into steps, each one of those steps could be a problem on the exam because each one of those steps is about a 6-minute type problem. So that's all I have. I'm happy to answer any questions. And then as you prepare for the exam, feel free to email me. Just remind me that you were on my webinar. Yeah. You're very welcome. And I really like to know if you pass the PE, so feel free to email me when you pass it, okay? I think you guys are off to a good start because you were following on those problems we were working, and that's a big chunk of what's going to be covered on some of the basic engineering part. So, and the other piece of advice is just be comfortable working in both sets of units.